and welcome to Programming C course. Before we continue with lesson number 2, I want to explain you about number systems. There are 4 number systems we will be dealing with. The first is binary, which consists of only 2 digits, 0 and 1. The second is octal, which consists of 8 digits from 0 to 7. And the third is decimal, which consists of 10 digits from 0 to 9. And lastly, hexadecimal, which consists of 16 digits from 0 to 9 and from A to F. These letters A to F can be in uppercase or can be in lowercase. In the given table, on the rightmost column, we see examples of these number systems. First, let us look at the binary. The example is 0100, 1100, and the base is 2. And the example of octal is 7520, the base is 8. In octal number system, the digit 8 and 9 cannot be there. Only from 0 to 7 can be there. In decimal number system, any digit from 0 to 9 can be there. And in hexadecimal system, any digits from 0 to 9 and letters from A to F can be there in the number. Now in the coming slides, I will tell you more about these number systems. Now, conversion of decimal to other systems. In this slide, we will be dealing with integer part only, not the fractional part. We will deal with fractional part in the next slide. Let us first do the conversion of decimal to binary. Suppose 39 is the decimal number we want to convert to binary. Since base of binary is 2, we will divide 39 by 2. When we divide 39 by 2, the quotient is 19 and the remainder is 1. So we write the remainder 1 alongside 19 in the third column. Then we divide 19 by 2 again. The quotient is 9 and the remainder is 1. We write the remainder 1 alongside 9 in the third column. And we divide 9 by 2 again. The quotient is 4 and the remainder is 1. We divide 4 by 2 again. The quotient is 2 and the remainder is 0. We divide 2 by 2 again. The quotient is 1 and remainder is 0. We divide 1 by 2 again. The quotient is 0 and the remainder is 1. Remember, even though at the last division there is 1, we have to continue division till the quotient is 0 and the dividend becomes the remainder. Now after this, we collect the remainders starting from the bottom towards the top. So the binary equivalent of decimal number 39 is equal to 100111. We will use the same process in conversion of any decimal number to octal and hexadecimal. In case of octal, we will divide by 8, and in case of hexadecimal, we will divide by 16. Now, the decimal number 553, let us convert it to octal. Since we are converting to octal, we will divide by 8. When we divide 553 by 8, the quotient is 69 and the remainder is 1. We divide this 69 by 8 again, the quotient is 8 and the remainder is 5. When we divide 8 by 8, the quotient is 1 and the remainder is 0. And then we divide 1 by 8, the quotient is 0 and the remainder is 1. Now we collect the remainders from bottom to top. So the octal equivalent of the decimal number 553 is equal to 1051. This is base 8. Similarly, we can convert the decimal number 751 to hexadecimal number. For this, we have to divide by 16. Let us divide 751 by 16. Now the quotient is 46 and the remainder is 15. In hexadecimal, we write 15 as F. So in the remainder column, we write F. Now we divide 46 by 16. The quotient is 2 and the remainder is 14. And in hexadecimal, we write 14 as E. Now we divide 2 by 16. The quotient is 0 and the remainder is 2. We continue this division process until we get 0 in the quotient. After that, we stop and collect the remainder digits from bottom to top. Now the hexadecimal equivalent of decimal number 751 is equal to 2EF. Now conversion of fractional part of a decimal number to other number systems. In order to convert decimal to binary or decimal to octal or decimal to hexadecimal, we multiply the fractional part in the decimal number by 2 till it is 0 in case of binary, by 8 till it is 0 in case of octal, and by 16 till it is 0 in case of hexadecimal. Let us first do the conversion of decimal to binary. Here we have to multiply the fractional part in the decimal number by 2 till the fractional part is 0. When the fractional part is 0, we end the process, we stop. First we multiply the decimal fractional part 0.625 by 2. The product is 1.25. We take out the integer part 1 and write separately in the fourth column. The remaining fractional part 0.25 we multiply again by 2. The product is 0.5. We take out the integer part 0 and multiply the fractional part 0.5 by 2. The product is 1.0. We take out the integer part 1 and the fractional part remaining is 0. Here we end the process of conversion. Now we collect the integer part from top to bottom. So the binary equivalent of the decimal fractional part 0.625 is equal to 0.101. Obviously, we are going to write a point before these binary numbers as we are trying to find out the fractional part of the binary. We follow the same process for conversion of any decimal to octal. The only difference will be we multiply the fractional part by 8 till it is 0. Let us take the decimal fractional part 0.45 and let us multiply it by 8. The product is 3.6. We take out the integer part 3, so the fractional part remaining is 0.6. We multiply it by 8 again. The product is 4.8. We take out the integer part 4 and the remaining fractional part is 0.8. We multiply it again by 8. The product is 6.4. We take out the integer part 6. The fractional part remaining is 0.4. We multiply it by 8. The product is 3.2. We take out the integer part 3. Remaining fractional part is 0.2. We multiply it by 8. The product is 1.6. We take out the integer part 1. The fractional part is 0.6. Here the fractional part remaining is repeating. So from step number 2 to 5 will be repeated again and again, and we will be getting the integer parts 4, 6, 3, 1 again and again. So the octal equivalent of the decimal number 0.45 is equal to 0.34631. Here I am underlining 4631 to indicate that 4631 repeats. Lastly, we'll convert a fractional decimal number to fractional hexadecimal number. Suppose the given decimal fractional number is 0.8. We multiply it by 16. The product is 12.8. We take out the integer part 12, but in hexadecimal we write 12 as C. So here we are seeing that the fractional part is repeating, and so the integer part we are collecting is also repeating. So we end the process here. Therefore, the hexadecimal equivalent of the decimal fractional part 0.8 is equal to 0.C. I am underlining the digit C to indicate that C is repeating. Now before we convert any given binary, octal or hexadecimal number to decimal number, first we have to know the place values of the digits appearing in the numbers. First, in decimal number system, we know place values to the left of the decimal point are ones place, tens place, hundreds place, thousands place, 10,000s place. These can be written also in the form 10 to the power 0, which is equal to 1, 10 to the power 1, which is equal to 10, 10 to the power 2, which is equal to 100, 10 to the power 3, which is equal to 1000, and 10 to the power 4, which is equal to 10,000. Now to the right of the decimal point, the place values are 0.1, 0.01, 0.001, 0.0001. These can be also written in the form 1 by 10 to the power 1, 1 by 10 to the power 2, 1 by 10 to the power 3, and 1 by 10 to the power 4, and so on. Similarly, in binary, instead of powers of 10, we will be having powers of 2. To the left of the point, the place values will be 2 to the power 0, which is equal to 1, 2 to the power 1, which is equal to 2, 2 to the power 2, which is equal to 4, 2 to the power 3, which is equal to 8, 2 to the power 4, which is equal to 16. In short, the place values in case of binary to the left of the radix point will be 1, 2, 4, 8, 16, and so on. And to the right of the radix point, it will be 1 by 2, 1 by 4, 1 by 8, 1 by 16, and so on. Similarly, in octal, which is base 8, the place values to the left of the point will be 1, 8, 8 square, 8 cube, 8 to the power 4, and the place values to the right of the point will be 1 by 8, 1 by 8 square, 1 by 8 cube, and 1 by 8 to the power 4. In case of hexadecimal system, which is base 16, the place values to the left of the point will be 1, 16, 16 square, 16 cube, and 16 to the power 4, and to the right of the point it will be 1 by 16, 1 by 16 square, 1 by 16 cube, 1 by 16 to the power 4, and so on. Once we know the place values of digits in binary, octal, and hexadecimal, we can now easily convert any number given in binary, octal, and hexadecimal to equivalent decimal number. Now, conversion of any other number system to decimal system. Before we proceed with converting binary, octal, or hexadecimal number to decimal number, let us first see how decimal numbers can be expanded using its place value. The given decimal number is 9860. It can be expanded using its place value is 9 into 10 to the power 3. 10 to the power 3 is its place value. 3 because there are 3 digits to the right of 9. Plus 8 into 10 to the power 2, its place value. 2 because there are 2 digits to the right of 8. Plus 6 into 10 to the power 1, its place value. 1 because there is 1 digit to the right of 6. And we ignore the last digit 0. So that's how we can expand the given decimal number 9860 in terms of its place values. So to convert any given number in binary, octal, or hexadecimal to its decimal equivalent, we will be multiplying its digit in the binary, octal, or hexadecimal by its place value and add all of them together, and we will get the decimal equivalent. First, let us convert the given binary number to its decimal equivalent. The given binary number is 01001100. The first digit is 0, so we ignore it. The second digit is 1. We multiply it by its place value. Its place value is 2 to the power 6. 2 because it is binary number system, and 6 because there are 6 digits to the right of 1. The next 2 digits are 0, so we ignore them. The next digit is 1, so we multiply it by its place value 2 to the power 3 because there are 3 digits to its right. The next digit is 1. We multiply it by its place value 2 to the power 2 because there are 2 digits to its right. The last 2 digits are 0, so we ignore them. So now 2 to the power 6 is 64, 2 to the power 3 is 8, and 2 to the power 2 is 4. We add them together and we get 76. So the decimal equivalent of the given binary number is 76. Next, let us convert the given octal number 7520 to its decimal equivalent. To find out the decimal equivalent, we multiply its digits by its octal place value and add them together, and what we get will be the decimal equivalent. So let us start converting it. The first digit is 7. We multiply it by its place value 8 to the power 3 as there are 3 digits to its right. The next digit is 5. We multiply it by its place value 8 square since there are 2 digits to its right. The next digit is 2, so we multiply it by 8 to the power 1 as there is only 1 digit to its right. The last digit is 0, so we ignore it. We add all these numbers and we get the decimal equivalent as 3920. Lastly, let us convert a given hexadecimal number to decimal number. The given hexadecimal number is F9A5. The first digit is F. We will multiply it by its place value. Its place value is 16 to the power 3 as there are 3 digits to its right. Plus the next digit is 9. We will multiply it by its place value 16 square. The next digit is A. We will multiply it by its place value 16 to the power 1. And the last digit is 5, and we will multiply it by 16 to the power 0, which is 1. Now before we start adding up these products, let us first convert the letters F and A to its decimal equivalent. Remember, F means 15 and A means 10 in hexadecimal. So we replace F and A by 15 and 10, find out the multiplication, then add them together, and we get the decimal equivalent is 63,909. So that's how we convert any given number in binary, octal, or hexadecimal to its equivalent decimal number. Before we start converting the given binary number to octal number, let me first remind you that if you convert any 3 digits of binary number to its decimal equivalent, that decimal equivalent will be its octal equivalent also, because the largest value that any 3-digit binary number can represent is 7, and 7 is within our octal number system. That's why if you convert any 3-digit binary number to its decimal equivalent, will be its octal equivalent also. Using this knowledge, let us convert the given binary number to its octal equivalent. Now we have already made these binary numbers into groups of 3, inserting zeros to the extreme right as well as to the extreme left if necessary. Now let us first convert the first groups of binary digits, that is 111. Its decimal equivalent is 7, so its octal equivalent will be 7 also. Now let us convert the second groups of 3 binary digits, 101. Its decimal equivalent is 5, so its octal equivalent will be 5. Now let us convert the third groups of 3. Its decimal equivalent is 6, because 4 plus 2 plus 0 is 6, so its octal equivalent will be 6 only. Then point will come, and the next group of 3 binary numbers after the radix point is 001. Its decimal equivalent as well as octal equivalent will be 0 plus 0 plus 1. The last group of 3 binary number is 100. Its decimal equivalent is 4 plus 0 plus 0, that is 4, and so will be its octal equivalent. So the equivalent octal number of the given binary number is 756.14. So this is pretty fast. How we did it? We make the binary number into groups of 3. If any group doesn't have 3 digits, then we insert zeros. Those zeros can be inserted only to the extreme left and to the extreme right, not in between. Then we convert its groups of 3 binary numbers to its equivalent octal number. Now let's come to conversion of octal to binary number. To convert octal to binary, we convert its octal digit to its equivalent 3-digit binary number. The octal number 6 is equivalent to the binary number 110, because 4 plus 2 plus 0 is 6. Now the octal number 5 is equivalent to binary number 101, because 4 plus 0 plus 1 is 5. The octal number 0 is equivalent to 000, because 0 plus 0 plus 0 is 0. The octal number 5 is equivalent to binary number 101, because 4 plus 0 plus 1 is 5. And lastly, the octal number 0 is equivalent to 000 in binary number. So we are converting its octal digit to its equivalent binary number of 3 digits. And here we go. We have finished converting the given octal number to its equivalent binary number. Let us now move to conversion of any binary number to hexadecimal and hexadecimal number to binary. Let us first convert any given binary number to hexadecimal. In order to convert any binary number to hexadecimal number, we make groups of 4 from the given binary digits, inserting necessary zeros to the extreme left in case of integer part and extreme right in case of fractional part to complete groups of 4 if it is not completed, and then convert its group of 4 binary digits to its equivalent hexadecimal digit. Let us look at the given binary number. I have inserted 3 zeros to the extreme right to complete groups of 4 binary digits. Now let us convert its groups of 4 binary digits to its equivalent hexadecimal number. Now let us convert the first group of 4 binary digits 111 first to its decimal equivalent. So its decimal equivalent is 8 plus 4 plus 2 plus 1. 8 plus 4 is 12. 12 plus 2 is 14. 14 plus 1 is 15. 15 in hexadecimal number is F. So the first hexadecimal digit will be F. Now let us take the second groups of 4 binary digits, that is 1011. Its decimal equivalent is 8 plus 0 plus 2 plus 1, that is 11. 11 in hexadecimal number is B. So we have got the second hexadecimal digit B. The next group of 4 binary digits is 1101. Its equivalent decimal number is 8 plus 4 plus 0 plus 1. 8 plus 4 is 12. 12 plus 1 is 13. 13 in hexadecimal number is D. So we have finished converting the integer part into hexadecimal number, that is FBD. Now comes the point. Then we convert the next group of 4 binary digits. 1001 in decimal will be 8 plus 1, that is 9. The next group of 4 binary digit is 1000. Its decimal equivalent is 8. So finally we have got the equivalent hexadecimal number FBD.98. That was relatively faster. If we didn't use this method, we would have converted the given binary number to its decimal equivalent, and from that decimal equivalent we would have converted it to its equivalent hexadecimal number. But here we have straightforward converted the given binary number to its equivalent hexadecimal number. Now we can do the reverse process, that is hexadecimal to binary, in similar fashion. Now to convert any hexadecimal number to binary number, we convert its hexadecimal digit to its equivalent 4-digit binary number. For example, the given hexadecimal number is C764.AF. C in hexadecimal number is 12. So we try to write 12 to its equivalent 4-digit binary number, that is 1100, because 8 plus 4 plus 0 plus 0 is 12. Next we write 7 in hexadecimal number to its equivalent 4-digit binary number, that will be 0111, because 0 plus 4 plus 2 plus 1 is 7. Next we write hexadecimal digit 6 to its equivalent 4-digit binary number, that will be 0110, because 4 plus 2 is 6. Next we write hexadecimal digit 4 to its equivalent 4-digit binary number, that will be 0100, because 0 plus 4 plus 0 plus 0 is 4. Then comes the point. The next hexadecimal number is A, which is 10. Its 4-digit binary equivalent number is 1010, because 8 plus 0 plus 2 plus 0 is 10. The next hexadecimal number is F, which is 15. Its equivalent 4-digit binary number is 1111, because 8 plus 4 plus 2 plus 1 is 15. That's how we convert any binary number to hexadecimal number, by converting groups of 4 binary digits to its equivalent hexadecimal digit, and hexadecimal number to binary number by converting its hexadecimal digit to its equivalent 4-digit binary number. This process of conversion is relatively faster. We could have converted from binary to hexadecimal by first converting to decimal, and then from decimal to hexadecimal, and from hexadecimal to binary by first converting to hexadecimal to decimal, and then from decimal to binary. But by making groups of 4 binary digits, we have made the conversion relatively faster. Now that we have learned the 4 number systems and how to convert among them, let us go to constants in C. Constants in C refer to fixed values that do not change during the execution of a program. The types of constants in C are numeric constants and character constants. Again, numeric constants are of 2 types. The first is integer constants and the second is floating point constants. Floating point constants means real numbers having decimal point or an exponential. Again, there are 2 types of character constants. They are single character constants and string constants. String constants have more than 1 character, whereas single character constants have only a single character. The following rules apply to all numeric type constants. Commas and blank spaces cannot be included within the constant. The constant can be preceded by a minus sign if desired. The value of a constant cannot exceed specified minimum and maximum bounds, as it should be, because its data type, whether it be char, int, float or double, they have a maximum value as well as a minimum value that can be stored in its data type. Now, what are integer constants? An integer constant refers to a sequence of digits. An integer constant may be a decimal or octal or hexadecimal number that represents an integral value. A decimal integer constant consists of any combination of digits from 0 to 9 preceded by an optional minus or plus sign. For example, minus 32,768, 5,280, 32,767, 9,999. Spaces, commas and non-digit characters are not permitted between digits. For example, there is a space between 15 and 750. This space is not allowed, illegal, or is not valid. The next example is 20,000. There is a comma in between. This comma is illegal or is not valid. In the next number, there is a rupee symbol in front of 1000. This is illegal or not valid. In the next integer constant, there is a decimal point, which is illegal or not permitted because it is an integer constant. An octal integer constant consists of any combination of digits from 0 to 7 preceded by a 0. Remember, any octal integer constant is preceded by a 0. For example, 037 is octal number 37, 0435 is octal number 435, and single 0 is octal 0, and 0551 is octal number 551. A hexadecimal integer constant consists of any combination of digits from 0 to 9 and letters from A to F, uppercase or lowercase, preceded by a 0x. In uppercase or lowercase, the letters A to F represent the quantities 10 to 15 in decimal. For example, the number 0x2 is the hexadecimal number 2. The number 0x9f is the hexadecimal number 9f. The number 0x.B.C.D. is the hexadecimal number B.C.D. The number 0x is the hexadecimal number 0. In all these numbers, we preceded its number by 0x to indicate that it is a hexadecimal number. Now, how to indicate an integer constant is unsigned or long integer constant. An unsigned integer constant can be identified by appending or suffixing the letter u either in uppercase or lowercase to the end of the constant. For example, u is appended to decimal integer constant 50,000 to indicate that it is an unsigned decimal integer constant. Similarly, u is appended to octal integer constant 777 to indicate that it is an unsigned octal integer constant. And u is appended to hexadecimal integer constant 49af to indicate that it is an unsigned hexadecimal integer constant 49af. A long integer constant can be identified by appending the letter L either in uppercase or lowercase to the end of the constant. For example, the decimal integer constant 1, 2, 3, 4, 5, 6, 7, 8, 9 to indicate that it is a long decimal integer constant. Similarly, L is appended to the octal integer constant 1, 2, 3, 4, 5, 6 to indicate that it is a long octal integer constant. Similarly, L is appended to hexadecimal integer constant A, B, C, D, E to indicate that it is a long hexadecimal integer constant. An unsigned long integer may be specified by appending the letters UL either in uppercase or lowercase to the end of the constant. For example, UL is appended to the decimal integer constant 1, 2, 3, 4, 5, 6, 7, 8, 9 to indicate that it is an unsigned long decimal integer constant. Similarly, UL is appended to the octal integer constant 777 to indicate that it is an unsigned long octal integer constant. And UL is appended to the hexadecimal integer constant 99FFF to indicate that it is an unsigned long hexadecimal integer constant. Now, how to indicate that a number is a floating point constant? A floating point constant is a decimal number that contains either a decimal point or an exponent or both. For example, 0 point. It is a floating point constant, not integer constant, because it is having a decimal point. 1 point. It is also a floating point constant, not an integer constant, because it is having a decimal point. 0.2. 827.602. The next number is 2e minus 8. This is a number in exponent form or scientific form. E means exponent. This number is equal to 2 into 10 to the power minus 8. This is a floating point constant. The next number is 1.667e plus 8. It means 1.667 into 10 to the power plus 8. This is also a floating point constant. The next number is 0.006e minus 3, which is equal to 0.006 into 10 to the power minus 3. This is also a floating point constant. Now remember, the following are not valid floating point constants. Let us see why. The first number is 1. It is not a valid floating point constant because it doesn't have a decimal point or an exponent. The next number is 1,000.0. This is not a valid floating point constant because it is having an illegal character comma in between. The next number is 2e plus 10.2. It is not a valid floating point constant because in exponent you cannot have a decimal point. Either it can be 10 or 2 but not 10.2. The next number is 3e space 10. It is not a valid floating point constant because it is having a blank space between e and 10. Blank space is an illegal character. Next, let us learn default values of constants. Integer constants by default represent int data type. We can override this default by specifying unsigned or long after the number by appending u for unsigned or L for long, respectively. Floating point constants by default represent double data type. However, it depends on the compiler also, meaning it may differ from compiler to compiler. If we want the resulting data type to be float or long double, we must append the letter F in uppercase or lowercase to the number for float and letter L in uppercase or lowercase for long double. Now let us come to numerical accuracy. Integer constants are exact quantities, whereas floating point constants are approximations. The floating point constant 0.1 in decimal may be represented approximately within the computer's memory in binary by 0.0001111001101. Now you can verify this whether it is true or not. Now, starting from the right of the radix point, as we move towards the right, the fourth digit is 1. Its place value is 1 by 2 to the power 4, that is 1 by 16. The next digit is 1. Its place value is 1 by 2 to the power 5, that is 1 by 32. The next two digits are 0, so we ignore it. The next digit is 1. Its place value is 1 by 2 to the power 8, that is 1 by 256. The next digit is again 1 and its place value is 1 by 2 to the power 9, which is equal to 1 by 512. The next two digits are 0 and the last digit is 1. Its place value is 1 by 2 to the power 12, which is equal to 1 by 4096. If you add up 1 by 16, 1 by 32, 1 by 256, 1 by 512, 1 by 4096, it is approximately 0.099853516 in decimal. So what you have to remember is the floating point constant 0.1 in decimal is stored approximately in binary number in the computer's memory, not the exact decimal 0.1, because it is not possible to store exactly in binary, because in computer's memory we are storing the number in terms of binary. But then when we print the number on the monitor, it may appear as 0.1, the exact decimal, because of automatic rounding. Therefore, floating point values cannot be used for certain purposes such as counting, indexing, etc., where exact values are required. Remember this, integer constants are exact quantities, whereas floating point constants are approximations in computer's memory, because we store the numbers in binary. In binary, it may not be possible to find the exact decimal equivalents, so we store in approximate values. Therefore, floating point values cannot be used for certain purposes where exact values are required. That's all for now. Thank you everyone.